Alright guys, let's see how we can draw the shear and moment diagrams for the loaded beam that we can see in here, and also we need to determine the maximum value of Mmax of the moment. So we're solving question from engineering mechanics, the chapter 5 by Meriam. And before we start going through the diagrams, we're going to start with finding the unknowns that we have at point A and B. And because we have a symmetrical beam in here, if we just want to show different forces that we have at point A, let's just consider the two forces that we need to consider for a pin, which is what we have at point A, and at point B we only have one roller. So since we are neglecting the effective friction in X direction, we only have a normal force, or By. So because of the symmetry, since we have also a distributed force on top, we're going to replace that by one single force, which is going to be, one side is 30 pounds per foot, which is the rectangle that we have, and the other side would be 4. So this is gonna give us 1200 pounds. This is also in feet, so the feet will be canceled out and will end up with 1200 pounds, and it will apply exactly at the center of this distributed force, which means this is going to be 2 on the left and 2 feet on the right side. So again, because of the symmetry, AY is equal to BY, and if we use our equilibrium equations, if we just do sum of all forces in X equals 0, we can figure out that actually AX is also 0, and we can do sum of all forces in Y direction equals 0, which would be 1200 downward, so negative plus, let's just call our X and Y in here, plus 2AY or 2BY is equal to 0. So AY in here would be same as BY, which is 1200 divided by 2, or 600 pounds. And we know that in these kind of 2D questions, we have 3 equations in total, Fx, Fy, and we have the moment equation. And if we just use that moment equation, and let's call this point C, and if we just do the sum of all moment about point C equals 0, we're going to get to this conclusion that AY is also equal to BY, which we already figured out by the symmetry of this beam. Okay, so the way we're going to draw the shear and moment diagrams in here is that we need to start with one side of the beam to the other side, and wherever we see a change in the force that are applying on that beam, that would be a hint for us that we need to try to divide this beam by those separate things. So for example, if we just, let me just clean up the figure. If we just move from point A toward B, and we can call this one actually our X, we can see that from 0, so this is our 0, from 0 to 4, we have the same story for the beam. And when we move from 4 to 8, this part, we're going to see our distributed force. And after 4 to 8, we're going to have different things. So what we're going to do is that we're going to try to section these in 3 different areas. And based on these 3 areas, we're going to draw our shear and moment diagrams. So let's start with the first portion where we are going from X0 to 4. And we're gonna deal with this part of the beam. So the right side is where we had our section. We already found A, or we called it AY, which was 600 pounds. And our section is somewhere up before where we have the distributed force, and we can consider here one shear force, we show it with V, and one bending moment with M. We also have an axial force, which we covered in the internal forces in the previous video, but we're not looking for that in this question, so I'm not going to show it. And that would be another force in X direction, which we don't need it in here. So let's start with our equilibrium equations. Again, we're going to do Fy, because we're going to have 600 minus the shear force that we are looking for, and from here we can get our shearing force 600 pounds, which shows moving from 0 to 4, we're going to have the same shear force, which is going to be V. So here, what we have for our distance, this will be our X, because this is our origin. So we are moving from 0 to X, and we're going to have the same value for our shear force. So if you just want to show the diagram in here, I'm going to show it like this. So we're going to show our shear force V, this will be our X, and we also need one for the moment. And I'm just going to draw some lines here just to show different parts of this So based on what we figured so far from moving on from 0 to 4 feet, we're gonna get the same value for our shear force, which is 600 pounds. So will be something like this in here. And this is 600 pounds. We can just show the units in here. And that's what we got for the shear force. Let's see what we have for the moment. And for the moment, we're gonna find the moment about where we did this section, or the point that we have in here. I'm gonna show it maybe with D. So we're finding the moment about D equals 0 counterclockwise, always positive. And we're gonna have the moment of the 600-pound force. And as we can see, it will be a clockwise moment. So negative 600 times X plus the moment that we have. And this will be equal to 0. And our bending moment here would be 600X. And for our moment, or our bending moment pound foot, we're gonna have a linear function. We'll get something like this. And if we want to find this point, we just have to put our x4, which is gonna be 600 times 4 or 2400. So that was the first part of this diagram, and we're gonna move on to our second section, which is the one that is in the middle. So when we have our x between 4 to 8, again, we have to consider one of the half of the beam. So we are doing this section, so we are dealing with the left side, and let's just draw the free body diagram for that side. So this was our section, and we have again the 600 pounds in here. The only difference is that we have our distributed force that is applying in here, and we know this part is 4, and we are calling this distance x, and what we're gonna have in here would be x minus 4. Same story for V and M. The only difference in here is that we have to deal with this distributed force, and let's do the same thing. Start with our sum of all forces in y equals 0. So we're gonna have the 600. We're gonna have our shear force, which is downward, and we also have the distributed force in here, which, as we saw, we have in here 300 pound per foot. But this time we're gonna multiply this 300 by, first of all, the force is negative, so it's gonna be 300 times the distance, which is x minus 4. And this will be equal to 0. Very similar idea to what we have when we were trying to find the distributed force. We kind of like finding the area of this rectangle. It's just we have a different side for this rectangle, which is the x minus 4. So based on this, we can find the function of v based on our x. So I'm just going to bring the v on the other side. It will be equal to 600 minus 300x plus 1200. So our v would be minus 300x plus 1800. So that's our function that we need to draw in our diagram. So we're gonna have a negative slope for this one. We have minus 300, and we're gonna start from this point just to double check that everything is good. We're just gonna put 4 in here, see if we get this 600 or no. And if we just do that, we're gonna have minus 300 times 4, which is minus 1200 plus 1800. So that's going to be 600, and that shows that we're good so far. And if we want to find the ending point, we know our ending point for x is 8. So we're just going to put 8 in here. So minus 300 times 8 plus 1800. So that's going to be minus 2400 plus 1800. That's going to be minus 600. So we're expecting to go somewhere in here when we are at x is equal to 8, which is minus 600. So we still have a linear curve because the function that we have is a linear function, and because of that negative slope, we're going to go in this direction. And let's move on to our moment, the moment curve. So for that one, we're going to do sum of all moments equals 0. Again, about the point that we did the section, we just call it D again. So we're going to have the M that we are trying to find, and it's counterclockwise. So positive, we have the moment of 600, which is a clockwise moment, so negative minus 600 times the vertical distance to the line of action, which is pretty much the x that we have in here. And also we have the moment of distributed force, and that would be counterclockwise, so positive. We figure out the force in the previous step. It was 300 times x minus 4. And as we know, this distributed force, we're going to replace it with one single force that has this magnitude, and it will be applied exactly at the center of this, which would be x minus 4 divided by 2. That would be our function. So m would be 600x minus 150 if you just cancel these two, and we're going to have x minus 4 squared, which is going to be x squared minus 8x plus 16. So our new function, we have to multiply this by each of this. So we're going to get minus 150x squared plus 8 times 150 is going to be 120x, or 1200x plus 600x. And that's going to be minus 2400 because it's twice as 1200. Yeah, sounds like we found our new function, and it looks like a quadratic function. So plus 1800x minus 2400, and that's going to be our function that we need to draw the graph. And if we look at this, we'll see that we have a parabola, and because of the coefficient of x squared is negative, our parabola opens downward, so we're expecting something like this. And that's why the question is asking for the maximum, because we have a parabola that opens downward. So for that part of this, we're gonna get something like a parabola, and let's just figure out how it's gonna end at point 8. All we need to do in here, just put 8 in our equation, see what we get. Minus 150 times 8 squared, which is 64, plus 1800 times 8 minus. So based on our diagram, we're expecting 2400. Let's see what we get. Minus 150 times 60 minus 150 times 64 plus 1800 times 8 minus 2400. And yeah, we got the 2400. So we are at the same level. And the last part of this question is where we are moving from x8 to 12, which because of the symmetry of this figure, we kind of can predict that this is going to feel like this, and our moment equation is going to go somewhere in here. And before going to this part, the question is asking for the maximum. If we get back to the question, so we have to find the maximum value of the moment, which in this case we're going to go with the derivative of m with respect to x in here. And if we do that from the first term, we're going to get minus 150 times 2x plus 1800, and we're going to put this equals 0. And when we do this, usually we get the maximum or minimum, but because our parabola opens downward, we're going to get the maximum. That's why the question is asking for maximum 2. So we're going to get minus 300x is equal to 18. So our x would be 6 feet. And if we just put the 6 in here, we're going to get our moment. We just have to put 6 in the moment equation that we had in here. So 150 minus 150 times 36 plus 1800 times 6 minus 2400. Let's calculate this. So minus 150 times 36 plus 1800 times 6 minus 2400, and that's going to give us 3000, which is going to be our maximum of the moment, pound-foot. And if we just get back here, the maximum that we have in the diagram is going to be 3000 pound-foot. And yeah, I'm just going to skip the last part of this because it will be very similar to what we did in the first step. I don't want to make this video too long, but like as a practice, you guys can try it, and what we get at the end will be what we have in here. And yeah, that's going to be the final answer for this question. Hope everything was clear, and you guys take care. I'll see you in the next video. Have a good one.